Science and engineering are involved in many areas of public decision making. Think, for instance, of environmental decision making. Science and engineering knowledges, however, are often hard to penetrate for decision makers and other actors. When disputes arise about what decision to take, the knowledges that supposedly underpin alternative decisions can also come under dispute. Take the example of cities, flooding, and climate change. What may happen in future with the climate-related risk of flooding in urban areas, and what can and should be done about it? Other questions. Will this risk increase in a particular location, such as South Asian megacities under climate change? To what extent can reduction of greenhouse gas emissions mitigate the risk over the course of this century? Can and should one take adaptation measures to handle the risk? Which measures then? So questions arise about socioeconomic developments, changes in institutional capacities, changes in socio-technical systems such as water systems, and changes in the physical climate system, which are all interlinked. How then to best make decisions under such a multitude of uncertainties, where values are at stake and the science is under dispute? How does one engage the different stakeholders and their perspectives? In this talk, I will focus on one part of the puzzle, the uncertainties in science and engineering that are relevant to a policy problem. How do you identify and assess these uncertainties? I take the notion of science broadly here, so it includes economics and other social sciences. Scientists and engineers face a huge challenge in bringing together the different types of knowledge necessary for informing decision makers. Natural science, typically quantitative knowledge, has to be integrated with social science, typically quantitative, but also qualitative knowledge. And this scientific knowledge needs to be further integrated with practitioners' knowledge. Each type of knowledge has different limitations and types of uncertainties attached to it. To give one example of scientific uncertainty, climate scientists are not able to model the behavior of clouds well enough to understand how the weather and climate will change in the future precisely. Real clouds are much smaller than the size of a grid box in a computer model of the climate system. So here you see a weather radar of the whole cloud system. You see large individual clouds in it. The global model and even the regional model of a climate cannot resolve everything that happens at the level of a cloud. So this means that climate scientists have to make assumptions about cloud behavior at the larger scales that they can model. But such assumptions can be made differently, and hence there is a large spread in climate model outcomes. Precipitation is typically one of the most difficult quantities to model. While peaks in precipitation are expected to increase under warming climates, for many areas the models disagree how much rain there will fall in particular seasons. Take the Netherlands, for example, shown here. Some models say that summer precipitation will increase, others that it will decrease. And this is just one example of uncertainty deriving from the natural sciences. There's also uncertainty if we think about climate change and its risks, about the future of socioeconomic developments. Those developments are often even more important. How many people will live where? And how will they live? So when we are interested in how to assess uncertainty for decision making, we must realize that there is more to uncertainty than statistics. I use the term reliability or unreliability here to make both a link to statistics and also be able to introduce two other dimensions of reliability. There are three ways in which reliability of findings can be assessed and expressed. And we're interested in answering the question, to which extent can one rely on a particular finding from a scientist or engineer? So if we look at statistical reliability, we focus at the range of uncertainty, typically expressed as, for instance, a 95% confidence range, with the idea being that the real value lies in that range to the extent that the statistics express that. But the second dimension is non-quantitative, it's qualitative, and it has to do with deeper uncertainties than you can assess through statistics alone. That's what I call methodological reliability, where you ask the question, what is the underpinning for the model or for an assumption in a model? Where does it come from? Which theory is behind it? What do other models say? Is there agreement in the scientific community? So those issues all cover what I call the second dimension of scientific reliability. And then the third dimension, which I call the public reliability, deals with the question of why should we trust this scientist or engineer? So that's a completely different dimension, but it plays a very important role when assessing the reliability of a finding and also its uptake and use in decision making. Now, the example I would like to highlight here is an example which derives from the Intergovernmental Panel on Climate Change, its Working Group 2 reports on impacts, adaptation and vulnerability. I focus here on the chapter on urban areas, and I pick two examples from a nice table in that chapter about water-related risks of climate change in Durban, South Africa, just to give a particular example and be specific. Now, what's highlighted in this table is a lot of information coming from many different publications, and so they are summarized here in this table. So for water supply systems, there is a part of a column in the table where the types of adaptation measures are highlighted. So in this case, there is demand and supply side management required in future. It's important to reduce water losses. It's important to use ecological infrastructure to improve the level of assurance of water supply. And in a way, there are already measures being implemented and considered. And I will tell you why. The risk is, of course, changes in precipitation that may pose stress on the system. At the present day, the present climate is already posing a medium level of risk. This is an expert judgment on the different levels of risk. So there's already a medium level of risk where the sense is that by taking measures, adaptation measures, it is possible to reduce those risks at present. The climate change in the near term will not lead to a step change, a step increase in these risks. But if we come to the end of the 21st century, we see that even for the optimistic scenario, where there will be significant mitigation of climate change, so reduction of emissions, and the warming will be limited to 2 degrees as compared with pre-industrial temperatures. So the risk would go up and become between medium and very high. Also there is a possibility through adaptation to lower the risk to stay within the medium range. However, if we end up in a 4-degree world, the projection of these climate scientists, and they do that with a high confidence, so this is a pretty robust result, is that it is not possible anymore to adapt to a world and the changes that come with that has a warming of 4 degrees. Similar things hold for the wastewater system. I won't go much into detail. Very important there is, of course, how to deal with the peaks in the precipitation, the extreme precipitation that are expected to increase. Now, where do all these uncertainties or all these factors, they are associated with large uncertainties about the future, about what can be done. Where do these uncertainties come from? How do they arise? Where in the analysis are they located? Now, in the science, both natural science and social science and engineering, you have models, you have data, you have experts that arrive at judgments, and those play a role in assessment of models and data as well. So always expert judgment is crucial in the practices of science and engineering. But uncertainties also arise in the assumptions that they make on the limiting, for instance, their system, their contextual assumptions. So this is an indication of the 4 locations in this practice of science and engineering where uncertainties may arise. But also in nature itself. Nature itself is a source of uncertainty. And that's, for instance, because of chaotic behavior in complex dynamical systems. There is a variability of the behavior of nature, which leads to a particular unpredictability, which is inherent in nature and a source of uncertainty. And finally, people, of course, are also variable in their behavior. But what's even more important and significant about people is that they are reflexive and that they hold a plurality of views. Now, this leads to a crucial relationship between uncertainty and ambiguity. Ambiguity being a fact of life, also coming into play when doing science or engineering. It's important to realize that there are many situations where ambiguity does play a role. Situations that can be viewed from 2 or more different frames of reference and lead to different perspectives. The traditional scientific approach favors a truth that is external, objective, immutable. But over the course of especially the last century, also within science and mathematics, another mode, which can be called a participative mode of approaching reality, has been found to play a central role. So we people, we are a creative species. We can look at things differently. And we have to be aware of that fact. And we have to be aware of our creativity. And we also have to be aware of that there being creative ways to deal with this fundamental fact of life. Now, at the science policy interface, this all plays out as well. All these different types of uncertainty that are relevant for dealing with problems, societal problems, and that derive from science, from engineering, they should be dealt with appropriately. But it should be taken into account that people will hold different perspectives on these problems. And thus we arrive at the situation where what I would call the method, or what you could also call the problem-solving strategy of post-normal science becomes very relevant. Now, in some parts of engineering or applied science, the uncertainties of the systems that you're dealing with and the stakes of the decisions that society takes are relatively low. And then you can just leave it to the engineer. The engineer will give the solution to the problem. If things become more complex, you can give it to a consultancy. They have their ways to deal with that. However, if the system's uncertainty becomes really high and the decision stakes become really high, you should look at other ways, other practices, for instance, under this label of post-normal science, to deal with that situation in a way that is able to deal with the uncertainties and the different values that are at play. Now, this is not a mode of working which is generally part of the training of a scientist or engineer. And I joined the PBL Netherlands Environmental Assessment Agency, or it was used to be RIVM, the Netherlands Institute for Public Health and the Environment, in 2001. And then we started applying this thinking about post-normal science to the practice of environmental assessment. And what we developed was a guidance for uncertainty assessment and communication. Now, in that guidance, it's very important to realize that if you are dealing with uncertainties, it's not only about mapping and assessing the relevant uncertainties and reporting the uncertainty information, though these activities are crucial and central also in the guidance. The new thing that comes into the picture from this whole philosophy of post-normal science, and to which we made our colleagues really more attentive, is that in doing an assessment, you have to reflect on the problem frame that you choose, for instance, in your report. What is the problem that you're trying to address? Are there different views? How is the problem related to other problems? What are the system boundaries that you apply? And then the whole matter of stakeholders who really have stakes. Do you know who they are? What their views and roles are? Are they perhaps even interested? Or are there possibilities to have them being engaged with doing your scientific or engineering assessment? A whole issue, a third issue, which is typically neglected if you would only focus on, let's say, the areas 5 and 6. A third one is the selection of the indicators. Which indicators are you selecting for representing the problem? For instance, the problem of climate change is often represented, and I just did it myself before, by one number in terms of the global temperature change. But you are actually interested in problems which are not represented themselves by that indicator. So how far can you go in finding indicators that are meaningful for making decisions and for which there's still information that makes those indicators not too uncertain, and you can really take decisions on the basis of information on those indicators. And then I arrive at the final point, the appraisal of the knowledge base. It's very important to realize that you have to define, if you do an assessment from science and engineering for decision making, that often the knowledge that you would want to have is not available. So you have to really realize, what is the quality of my assessment that's really required? Where are the bottlenecks in the available knowledge and methods? And are there ways in future to deal with that? And then, of course, when you are ready, you have done all those steps, and you are really going to depth into determining what are the relevant uncertainties, and you are also addressing it in your report, and you are formulating your conclusions in a way that are robust for those uncertainties. You will also have to be robust for the knowledge gaps and communicate about that. Now, there are often so many aspects to a problem with information coming from natural science and social science, both quantitative and qualitative. How can analysts bring all this together? Are there methods available for doing that? Well, yes, there are. For example, originally developed in the environmental arena, there is the practice of integrated assessment. Many definitions can be given of integrated assessment. I refer listeners to the paper that's highlighted at the bottom of the screen. And many definitions can be given, and here's the shortest one that I could find, also coming from this publication. Integrated assessment is any decision-making related assessment in which some form of integration occurs, and it is done to support decision-making. Now, this definition in itself is perhaps not as informative as you would like, but to give you a little bit more flavor of what it can be and what it can do, integrated assessments They are a way to bring science and engineering information in a public policy setting, and it can be done and organized differently depending on the role that you want to give the assessment. For instance, if you have already a policy goal and you have already proposals available and you want to have an integrated assessment of whether the proposal will help to reach the goals, then you can end up typically with a relatively straightforward, involving not too many disciplines, a quick process, very technical way to make an integrated assessment which is as integrated as you need for that type of incremental decision. Think, for instance, of environmental impact assessment of a project. Now, there are also ways to look at futures which may be baseline led, where you're interested in the expected impacts of particular developments, for instance, of continued emissions of greenhouse gases. There are also more normative ways to do integrated assessment. One model can be integrated sustainability assessment, which is very multidisciplinary, has a wide scope of assessment. It typically involves a long-lasting process, maybe multiple years, is deliberative in nature, and is focused at transitions in society. To conclude, I would like to highlight one final aspect that should be considered when bringing science and engineering to bear on public deliberation and decision making. That is, analysts should be reflexively aware of the governance setting. Who produces the knowledge? Who uses the knowledge? Which filters apply? Besides getting the facts right, you will need to select the right facts. And for that, the governance of the whole scientific advisory process needs to be right in order to gain credibility, legitimacy, and salience for your assessment. In the end, it should be a co-production between the knowledge producers and the knowledge users.